There is yet another class of problems called optimization problems that has been mentioned in your syllabus. So to introduce this to you, I'm going to consider a very simple example that may be of interest to chemical and environmental engineers. We will not get into this topic in great detail through this course, but the one that I'm going to describe to you now will carry enough features of the optimization problem so that you can apply it in other situations if you have to. Optimization is a very fundamental technology that all engineers should learn. In fact, many things that we do in life relates to some kind of optimization, whether it is in our personal capacities as people, family members, members of society, or as engineers. We do optimization all the time. So let us look at this area a bit formally. Now, environmental engineers are concerned about pollution levels in rivers and other water bodies. So what we will do here is we will consider a very simple river system which has got a main flow which is like this, and then to this main flow you have other tributaries joining. So this you can say is one of the tributaries, and also we have many cities, right? 4 cities are shown here. Each of these cities generate waste and they want to discharge it to the water bodies. But then the government has laid out some regulations saying that if the concentration of that pollutant exceeds a certain quantity anywhere in the river system, the cities will be penalized. So it is up to the cities to process the waste at least to a certain level so that they keep the water body within the environmental regulation limit. So the cities will incur a cost for treating the pollutant. So the question is, how much of the pollutant should each city process? All of it? Half of it? 10% of it? That's what we got to find out. But the idea is the cities operate their wastewater treatment plants in such a way that the environmental regulations are met. So we will look at the terminology, what each of these symbols that are given here means in the next slide. But you can see you start with clean water in 2 places, right? You start with clean water and there are many junctions. As you can see there are at least 4 junctions marked 1, 2, 3 and 4 in which the waste streams from the city comes and joins the clean water and pollutes it. So city 1 produces pollutant amount P1 and then it has a wastewater treatment plant WWTP1. So it is associated with city 1. So in that treatment plant a good amount of the pollutant is removed and what is discharged into the river body is W1. Likewise, city 2 produces pollutant quantity P2 and that pollutant quantity is treated in a wastewater treatment plant and W2 is what gets discharged into the river. City 3 similarly produces P3 and using the wastewater treatment plant, it removes some of that pollutant and discharges W3 into the water stream that joins at junction 3. And city 4 produces pollutant amount P4. After the treatment in the wastewater treatment plant 4 that is dedicated to that city, W4 amount of pollutant is discharged into the river and the discharge from the wastewater treatment plant 4 joins the river at junction 4. So the points where the wastewater treatment plants discharge the pollutant into the water body, those are the 3 junctions that we need to take a look at. All right, so this is one aspect of it. The other aspect of it is that as the water flows from, let's say, junction 1 to junction 3, or from junction 2 to junction 3, or from junction 3 to junction 4, what is going to happen is natural biological processes remove some of the pollutant, right? So as the stream flows, there is a certain amount of pollutant that is removed from the water body. So nature plays its role as well. Okay, so this is another phenomena that's happening. And the symbols Q13, Q23, etc., Q34, Q45, all of these denote the volumetric flow rate of water in the water body between those junctions. So Q13 is the volumetric flow rate of the river between junctions 1 and 3. Between junctions 3 and 4, the volumetric flow rate of water in the river is Q34. Between junctions 2 and 3, it is Q23. That's the volumetric flow rate. And leaving junction 4 is the volumetric flow rate Q45. There are no temperature effects here, so you might understand that if you make a model for the steady state operation of the system, you're going to look at mass balances, right? You're not looking at energy balance here because there are no temperature effects that are assumed. So we are going to look at mass balance at junctions 1, 2, 3, and 4. And we'll have to write models that combine these symbols, most of which is displayed here. But let's look at the nomenclature that's adopted, the symbols and the meanings in this particular figure, right? So this is the figure that you have to pay attention to. And let me remove all the ink from there so you can see the figure clearly. And let's look at the symbols and meanings. So WWTP refers to the wastewater treatment plant. So potentially every city has a wastewater treatment plant to process the waste that it generates. Okay. So PI is the waste generated by city I in milligrams per day. So P1, P2, P3 and P4 like you see in this figure. So city 1 produces P1 milligrams per day. City 2 produces P2 milligrams per day of the pollutant. City 3 P3 milligrams per day, and city 4 P4 milligrams per day of the pollutant. Now WI, I going from 1 to 4, that means I takes values 1, 2, 3 and 4, denotes the waste discharged by city I. Okay, and it is very clear from the figure. W1, W2, W3 and W4 are the waste discharged or the pollutant discharged by the city I in the units of milligrams per day. So some of the pollutant that city 1 produces is treated in the wastewater treatment plant, and what escapes from wastewater treatment plant 1 is W1, which gets discharged into the water body. Similarly for city 2, city 3 and city 4. So these are the wastes that are discharged into the water body from the wastewater treatment plant of each city. And the units for W1, W2, W3, W4 are all milligrams per day. Now Xi denotes the fraction waste removed by the wastewater treatment plant. These symbols, right, may not be given to you. So one aspect of modeling is that you introduce symbols and their meanings so that you can write good mathematical models of the system. That is what you will do when you develop and become a very good modeler. But at the university level, sometimes these symbols and their units are given to you so that you can work with them. So Xi is the fraction waste removed by wastewater treatment plant I. So X1 will be the fraction of waste removed by wastewater treatment plant 1. As you can imagine, you can write Wi is equal to 1 minus Xi times Pi. Please note Xi is a fraction and it is dimensionless. And if Xi is equal to 0, Wi is going to be equal to Pi. Right? That means if the fraction waste removed by the wastewater treatment plant is equal to 0, then whatever pollutant that city produces is going to find its way into the water body because Wi would be equal to Pi when Xi is equal to 0. If the fraction waste removed by the wastewater treatment plant Xi equals 1, so Wi will be equal to 0. If Xi is equal to 1, Wi will be 0. That means all the pollutant that is produced by the city I is handled by the wastewater treatment plant I perfectly. So this equation should make sense given the descriptions of Pi, Wi and Xi. The next symbol we'll introduce is Ci is the concentration of the pollutant at the four junctions. So C1, C2, C3 and C4 are the concentrations of the pollutant at junction I. And the units would be milligrams per liter. So for every liter of water that you collect at these junctions, you will have the amount of pollutant there to be so many milligrams. So per liter, how many milligrams of pollutant can you find? So that concentration is denoted by the symbol Ci. So Ci is in units of milligrams per liter. As I stated earlier, Qij denotes the volumetric flow rate between junctions I and J. So Q23 will tell us the volumetric flow rate between junctions 2 and 3. And the units are in liters per day because it is volumetric flow rate, and we have used the day as the basis of time. It's not in minutes, it's not in seconds, it's going to be in days here. Rij denotes the fraction of pollutant remaining as the river flows downstream from junction I to junction J. So I already mentioned the pollutant level gets reduced due to some chemical and biological decomposition processes as the water flows, maybe through the action of sunlight, maybe through the action of microbial organisms in the water. So what happens is as the water flows from junction I to junction J, there is going to be a reduction in the pollutant quantity. So this Rij is a dimensionless variable that denotes the fraction of pollution or the pollutant remaining as the water flows downstream from junction I to junction J. So if Rij is equal to 1, the biological action or the chemical action has not happened and there is no reduction in the amount of pollution. If Rij is equal to 0, that means the biological decomposition processes have been great so that nothing remains. And finally, there is a cost of wastewater treatment, right? There is a cost of waste treatment in each plant, right? In each wastewater treatment plant, there is going to be a cost of waste treatment, and the cost is denoted in dollars per milligram. So if I remove 1 milligram of the pollutant, it is going to cost me DI dollars. That's what it means. So these are the symbols and these are the meanings for those symbols, and we will see how to make use of it when we write our model. And please note the environmental constraints or the environmental regulations is going to say that the CI, the concentration of pollutant at junctions, should be less than a certain amount, should be less than, let's say, 20 milligrams per liter, right? Because the concentrations in the water body is expected to be maximum at the junctions where the waste gets discharged from the four cities. So the government is right in saying at those junctions, the concentration of pollutant should not exceed a certain value. It must be lesser than or equal to a certain value that is decided by the dialogue between the government and the industries or the city councils, etc. Let's take this forward.